All right, good afternoon, folks. It's good, well, I guess you seeing this. I'm not seeing you here on this Monday afternoon. So check it out. We're looking at problem number 1 from the angular projectile motion problem. And I remember I'd left you off with asking you to try to figure out what would be an appropriate diagram for this particular problem. So once again, we have our jumper, stuntman jumper, going from the top of one building to another. We have an initial speed that was given to us, and we also had our angle theta, the distance and height between the two buildings, and our displacement horizontally. All right, now here's the thing with this problem. With problems before, you've been dealing with projectile motion where your initial and final displacement horizontally or vertically speaking is equal to 0. But with this particular problem, you have a negative vertical displacement, okay, where our final spot and our initial spot are not in the same plane. All right, they're different. Okay, so the key to getting this guy to work out is if your delta y, which we're trying to solve for with this particular problem, they gave us the y max, but if the y that you're going to be solving for in this problem is less than your maximum y, which is the heights there, and I guess it's less negative if that's the way to look at it, then our stuntman's going to make it, okay? So the variables we're working with, initial speed, they give us the angle theta, we know our displacement in the x, the y max, that's the one, we've got to have a value that's less than, or I guess less negative, smaller than this in the negative magnitude, and we're going to be trying to solve for y, and another item that we know is the acceleration in our y component, okay, which is that negative acceleration due to gravity, negative 9.8 meters per second squared. Now, since we're trying to solve for our y component here, we start with this kinematic equation right here, and then we change our variables to the y. Nothing new. You've seen this before. Now, since this is angular, we can solve for our initial speed in the y by looking at this triangle setup, where you've got your y, x, and then just your resultant vector, the overall speed from the problem that we had here. Now, you can solve for this by using the sine function, where you have opposite being y, and hypotenuse being the x1, and just plugging in the appropriate items, cross multiplying, and so your initial speed in the y can be plugged in to this equation from the kinematic equation where we just changed to our y's, and you get this guy. Now this is what we're trying to solve for, our displacement in the y, all right, for this particular problem. What's going to be our actual stuntman's, what's the minimum he's going to need. We know our initial speed, sine theta, we have that theta. We don't know the time. We know our acceleration y, and again, we don't know the time. So we're going to need to solve for time before we can actually solve for our y. So when we look over here, the equation that we normally use for the x component, the other equation that has time in it, is this guy right here. When we change to our x component variables, all right, our x component, we just are changing our speed for saying initial speed in the x, because you can change to initial or final whenever you're particularly interested in a problem, okay? Then, when you cross multiply like we've done before, you can say, oh, I know my delta x is equal to my initial speed in the x, and with our time. So we can solve for the initial speed in the x by, again, setting up that triangle we saw earlier, using the cosine function, adjacent over hypotenuse, plugging in. We get this guy right here can be plugged in, and then when we plug this guy in, we get our delta x equals initial speed, which we have from the problem given to us, cosine the theta we know, and then we can also solve for time now since we know our x displacement was a given in the problem. So we plug this into this, and you'd be good to go. Don't forget to also do your your dimensional analysis, or I guess unit analysis, and also before you do the substitution and solution step, okay? So go ahead, and after you get done with the assessment, if you finish it early, or you can certainly do it as homework, finish up number 1 and go ahead and do the rest of the problems on your own, okay? I think you should find them to be a little bit easier than this first problem that was tricky because of diagramming. All right. Great, good luck.